So up to this point, we've been looking at the descriptive question and looking at effect sizes, or how do we describe the strength of relationship between X and Y. And we haven't yet talked about the inferential question. If I get my parameter estimate, say my slope for my study, how well does my slope describe the true population parameter? So if I have the slope for my study, beta 1 for study S, we can say here's the slope for my study is equal to the true population parameter plus this error. Now this is not, we've been up to this point talking about the errors for how far people's observed score deviate from their predicted values. Now we're going to shift to how far does my parameter estimates for my study deviate from the true population parameter. And we're going to ask these two questions, which these questions should give you kind of deja vu. We were asking them in previous unit. So the one question is, what is the average size of these errors? So if we want to know on average, how far does each study deviate from our true population parameter? If we replicate our study over and over and over again an infinite number of times, on average, how far does each slope that we get from our studies, how far does each slope typically deviate from the true population parameter, beta? How much mistake do we make if we replicate our study over and over again? What's the average size of those errors? And again, what statistic answers that question? What tells you the average size of the ease for the deviation for how far statistics from studies deviate from population parameters? And that is going to be the standard error of the statistic. In this case, the beta weight. So the standard error of the beta will be how far, on average, the betas from our study, if we replicate our study over and over again, how far will the beta, the statistic from our study, typically deviate from the true population parameter? And then we can ask the second question, which is, if the null hypothesis is true, what is the standardized error for this particular study? And again, if you recall, what is the statistic that answers that question? It's the same one we've talked about before that answers that question, and that is the t-test. The t-test tells you, for this particular study, if I assume the null hypothesis is true, if I assume this beta weight is 0, if I assume the relationship is a 0 relationship between X and Y, if I assume there's no relationship, how much error did I make in the study in standardized units? What is the standardized error for this particular study if the null hypothesis is true? And we get that from a t-test, and a t-test is always a statistic divided by its standard error. So if we take this beta weight divided by its standard error, we will get a t-value. And with a t-value, there's always a question of, can I give you a formula you can use to calculate the standard error? And indeed, I have one right here. Here's the standard error of beta. If you use that formula, plug it in, you will calculate the standard error of the beta. And then if you take the beta divided by its standard error, you will get a t-value. So again, a t-value is a beta divided by its standard error, just as a t-value is always a statistic divided by its standard error. So the t-value for a beta weight is the beta divided by its standard error. And then when I say that, the next question is, well, is there a formula you can use to calculate the standard error of the statistic, in this case, the beta? And here is the formula for calculating the standard error of a beta. This is actually a rather nifty formula because it has actually three different components of that googly-eyed sheep table are all in here. So the standard error of a statistic is equal to that standard error of estimate, how far people's observed scores deviate from their predicted values on average, divided by the standard deviation of X times the square root of n minus 1. So again, the standard error of the beta, that's sampling error, is equal to the standard error of estimate, that's estimation error, divided by the standard deviation times the square root of n minus 1. And then so if you calculate the standard error of beta, once you do that, and actually for the most part, we're going to be letting computers do those equations for us. If you get that standard error of beta, you can take the beta divided by its standard error, you have a t-value, and then once you have a t-value, you can determine what is the probability of that t if the null hypothesis is true. And to determine that, you need to know degrees of freedom, because a t is a formula that has a known mathematical shape if the null hypothesis is true, but that shape changes shape slightly depending on how many people you have in your sample, or more accurately, it changes shape depending on your degrees of freedom. So to get probabilities of t-values, we need to know degrees of freedom. And in this case, our degrees of freedom are n-2. It's the same degrees of freedom we used for calculating the standard error of estimate, which we did earlier in this unit. And we use the same degrees of freedom here because we have an x variable and a y variable. We've calculated means for both, so we've lost 2 degrees of freedom. So our total degrees of freedom is n-2. So if you calculate a t-value, beta divided by its standard error, and then know your degrees of freedom, n-2, you can go to a t-table, or you can go online, use a t-calculator, or use a software package, and from that we can determine what is the probability of this t-value, assuming the null hypothesis is true. And as always, if the probability is less than 0.05, we reject the null hypothesis and say we have a significant result. And if it's not less than 0.05, we say our result is not significant. And we fail to reject the null hypothesis, and we feel very sad because we failed to find anything in our study. So that's significance testing for beta. What about the correlation? We can also test the significance of our correlation, because we talked about the correlation is another way to talk about the relationship between x and y. So we can take the correlation divided by its standard error and get a t-value for the correlation. Same procedure, just we have a different correlation is not going to be identical to our beta weight, so unless we've standardized everything, but if we haven't standardized things, then this could be a different correlation. So this is correlation divided by its standard error. And as always, we go through this process to say the t-value is equal to a statistic divided by its standard error, and then you say, is there a formula I can give you that you can use to calculate the standard error of that statistic? And I say, why, yes, here it is in the case of the correlation. Here's the formula right here. And I might note that in projects and quizzes and homeworks and tests and things, there's probably a lot more instances where you will need to calculate the standard error of a correlation than the standard error of a beta. So this is a formula you definitely need to be familiar with. So the standard error of a correlation, we take 1 minus our squared correlation divided by n-2. That's the exact same degrees of freedom we've been seeing all along here. And then take the square root, and that is the standard error. You just plug that formula in, and that will give you the standard error of the correlation. And again, the standard error of a statistic tells you if you replicate your study over and over again an infinite number of times, how far will your parameter estimate, your statistic that you get from your study, how far will your statistic typically deviate from the true population parameter? How much mistake will you make? How much will your study typically be off from the true population parameter if you replicate your study over and over again? That's that standard error of the statistic. And the t-value is your statistic divided by its standard error, which gives you the amount of error that you made in your study in standardized units, assuming the null hypothesis is true, which is the t-value. And then once you have your t-value, you can determine the probability of your t-value. You need to know degrees of freedom. That's the same as we've been looking at before, n-2, which are degrees of freedom. And if you know degrees of freedom in your t-value, you can then use a t-table, or go online, find a t-calculator, or use software, or if you wanted to use your own calculus, you could do it yourself. But you can determine the probability of the t, assuming the null hypothesis is true. If the probability is less than 0.05, you reject the null hypothesis and say you have a significant result. And if it's not less than 0.05, you fail to reject the null hypothesis. And again, you feel very sad because you failed to discover anything. Now, one thing that's important to keep in mind, and this will be very useful to you, especially in doing some of the homework and test and quiz type of questions that we have for this class, is that the t for a correlation divided by its standard error, back up a slide, will always be the same as a t for the beta, at least in our current unit when I have just one predictor and one outcome. When I'm doing simple regression with just two variables, one predictor, one outcome, then the correlation and the beta weight are both answering the same question. Both the correlation and the beta are answering the question, what's the strength of relationship between X and Y? And so the significance of the correlation is going to be the same as the significance of the beta because they're both answering the same thing. So if you take a beta divided by the standard error of beta, or if you calculate the correlation divided by the standard error of the correlation, a t-test for a beta, a t-test for a correlation, in this unit where we have just one predictor, one outcome, we have just two variables, then the t-value for the correlation and the beta are going to be identical. And so if you calculate the t for the correlation, you don't need to calculate a separate t for the beta weight because you know it's going to be identical. It'll be the same thing. So we've seen that we could calculate a t for correlation, we could calculate a t for beta, and it's going to give us the same thing. Is there something else we can do that would also give us the exact same thing? And the answer is yes. I've got one more thing to show you that will also calculate significance. It will be something we can use to say what's the relationship between X and Y and calculate the significance of that in an inferential statistic to give us information about how close the results from our study come to the true population parameter. And I'm going to shift now to a totally new topic called analysis of variance. And so analysis of variance is sometimes abbreviated ANOVA or sometimes called ANOVA. In some contexts, sometimes people talk about analysis of variance, and they are primarily talking about using an analysis of variance or ANOVAs when they're doing group comparisons. We're going to be talking about it in the context of regression, and it's actually all the same thing. Later on, we'll look at group comparisons and see how it's the same exact analysis, except for when we shift to group comparisons. For some reason, in the history of statistics, people didn't get together and decide to be consistent how they named things, and so some of the names of things in this table are actually going to change names when we do group comparisons, but it will be the same math. So I want to introduce this idea of analysis of variance, and for the moment it's going to do the same exact thing we did with a t-test. In other words, in this case we're going to calculate something called an f value. Instead of a t, we're going to calculate an f. And an f is just like a t in that it's a distribution, and it has a known shape if the null hypothesis is true. So just like the t distribution has a known shape if the null hypothesis is true, so also the f distribution there's a formula we can use to calculate an f. And when we calculate that f, if the null hypothesis is true, and we replicate our study over and over and over again an infinite number of times, we know exactly what the shape of that distribution will be. And so if we calculate a t-test for a study, we can look at the probability and say, what's the probability of this t-value if the null hypothesis is true? We can do the exact same thing for an f. We can calculate an f value and then look that up and determine if the null hypothesis is true, what is the probability of getting this f value? And as you might guess from how I've been setting this up, if we do that in our current example where I have one predictor and one outcome, the probability we get a p-value for our t-test will be identical to the p-value we get for the f. They won't actually quite be the same values. The f and t are going to be slightly different, but the p-value for the probability of the f will give us the same probability as the probability for the t-test. And once again, this is something I'm giving us to set us up for future units, because at the moment this is just going to be redundant with a t-test. But for future units, a t-test can do one thing, but an f-test is more flexible. There are things that an f-test can do that a t-test can't. And again, it's going to go back to that issue of omnibus versus focused. If I'm asking a question that's focused, what I mean is a question that I can answer with two hands. Say, is one variable associated with another variable? Is there a correlation between two variables? That would be a focused question, a question about just two variables, something I can answer with two hands, versus an omnibus question where, say, I have three predictors, and I want to say, do these three different predictors explain variance in a single outcome variable? I think the example I've been using throughout this unit is if I want to know if how much you wash your hands and how much you sleep and how much you exercise all predict health. If I want to know how much variance in health is explained by all three of those predictors, that would be an omnibus question. And a t-test cannot handle that type of omnibus question, but an f-test can. So the reason why I'm going to be talking about analysis of variance is that it is something more flexible than a t-test. If I just want to ask a focused question, is there a correlation between two variables? Actually, the simplest thing to do is just calculate a correlation and do a t-test to test the significance of that correlation, and that's the simplest way to go. But I want to talk about f-tests now because that will set us up for doing bigger and better things later on. So let's see what this f-test is all about. So to calculate an f-value, that's what we want to do. So analysis of variance is a process that's going to lead to the calculation of an f-value or an f-statistic. And once we calculate that f-statistic, we can then determine the probability of that f if the null hypothesis is true, because the f is just like a t, is that it's a distribution that has a known shape if the null hypothesis is true. And to calculate the f, we typically use this f table. So this table I have in the top half of the slide is called an f table. And the process of calculating an f value involves filling in values into this f table. And once we've filled in all the values into this f table, we will have our f statistic. So we have 3 columns. The first one says sum of squares. And so the first step is we need to calculate our sums of squares. And we need to calculate the sums of squares total, the sums of squares error, and the sum of squares explained. And we've already done that. Go back up, maybe I'll back up the slides here. Where is that previous slide? Here we go. This slide right here, this was summarizing after we calculated all of our sums of squares. Our total sums of squares was 700. Our error was 380. Our explained was 320. So we've talked about total variance sums of squares, error sums of squares, and explained. And we need these values to calculate an f. So I'm just going to take those 3 values and let's see, go over here's our, whoops. Actually, here we go. So I'm going to take those 3 values and put our total right there and the error there and the explained there. Make sure, yeah. So now at the bottom half of the slide, I've just copied the slide I showed you for how we calculate the standard error of estimate. Going way back to the beginning of this unit, we talked about how the standard error of estimate is the sum of y minus y hat squared, which is similar to total sum of squares, which is y minus y bar squared. We can calculate a variance, which is the total sum of squares divided by n minus 1, and the mean squared error, which is the total sum of squared error divided by n minus 2. And so parts of this table, that we talked about this a ways back, if you recall it. If not, you can scroll back and review that section where we were talking about how to calculate the standard error of estimate. But pieces of this are going to get plugged in. So our total sums of squares is this value here. The sum of y minus y bar squared is what gets plugged right there. And our sum of squared error, that's the sum of y minus y hat squared, is what gets plugged in right there. Now we could calculate our sum of square explained variance, which is the sum of y hat minus y bar, and put that there. Or at this point, if I have my total and I have my error, which sometimes it's easier to calculate those two things, I can just take total minus error and put that here, which is sum of squares explained. Or if I had sum of squares explained and my total, I could take total minus explained to get error. Either way, explained plus error always sums up to total. So that's my sums of squares column. And then the next column, I need to calculate my degrees of freedom. And we've already talked about a few of these. So my total degrees of freedom, that's for my variance right here, is n minus 1. And for my mean squared error, recall that that was n minus 2. And I'm going to clarify things just a bit here to make it more precise. So rather than saying n minus 2, I'm going to say it's n minus number of predictors minus 1, where p over here says p is number of predictors. So n minus number of predictors minus 1 is going to be my degrees of freedom for my error sums of squares. And it's always going to work out that explained plus error equals total, or total minus error equals explained. And so if my total degrees of freedom is n minus 1, and my error is n minus p minus 1, then my explained must simply be equal to p, which is number of predictors. Now, in our current unit, where I have just one predictor and one outcome, it's fairly easy. P is going to be equal to 1 if I just have one predictor. In later units, we'll have more than one predictor, and then we'll need to pay attention to what this is. But for the current unit, if I just have one predictor, it's simple regression, just one predictor, one outcome, then my degrees of freedom for explained will simply be 1. Then I need to calculate my mean squares. Note we're just following the same process. We've actually done this before. So we take our sums of squares divided by degrees of freedom to give what we'll call the mean square. Now, if I wanted to, I could put a box right down here in the lower right-hand corner there, and I could calculate my variance, my total sum of squares divided by n minus 1, and put it right there. It would follow the logic of the table to do that, because what we're doing, we're going to take the sum of squares divided by degrees of freedom to get a mean square. And so my total variance sum of squares divided by degrees of freedom gives me the variance, and it would make sense to put it right there. The only reason why I don't do that is we don't need that value for calculating the F statistics, so people typically leave that off. But if you felt, if it made you feel uncomfortable to have a table that feels incomplete and have something missing, and you like the idea of wholeness and like to see everything there and complete, maybe kind of that obsessive compulsive type of feeling where you just want to have everything filled in, if you feel that way, it would make logical sense to put your variance right there. But we don't actually need that for our formula. What we do need is to take our error sums of squares divided by its degrees of freedom to get our mean squared error, which is identical to what we already did when we talked about calculating the standard error of estimate, where we calculated our mean squared error. We took our total sums of squared error divided by degrees of freedom to get a mean squared error. And I'm just going to put that right here in that cell right there. And and this will be kind of a fairly easy thing for this. Well, I can take my total sum of squares divided by degrees of freedom to get my mean square explained variance, which for our current unit, when I have just one predictor, it's just explained variance sums of squares divided by 1, which is going to be explained variance sums of squares, so that same value gets put right there. In future units, that'll get more complex as we have different numbers of predictors, but for right now, that just comes out to be the same thing. So explained variance sums of squares divided by number of predictors, which in this case is 1, gives us my mean square explained variance. And now the F value is simply a ratio. You simply take the mean square explained variance divided by mean squared error. That's what it says right here, mean squared explained divided by mean squared error, and that gives you your F value. And once you've calculated that F value, you can then determine the probability of that F if the null hypothesis is true. Now, actually, before I go to that slide, let me just note that just like a T, an F is a family of distributions. So a T is not just a single distribution, but it's actually a family of distributions that changes shape just slightly depending on your degrees of freedom. And the F is the same thing. It's actually a family of distributions that changes shape just slightly depending on your degrees of freedom. Actually, the F changes a little bit more than the T does. So I should say the F changes actually in some ways quite a bit depending on your degrees of freedom. But one thing for the F is that we've got a couple different degrees of freedom to pay attention to, and we need to know both. So we have what I'll call my degrees of freedom for explained variance. And explained variance in our formula is the numerator. So I'm going to call this degrees of freedom numerator. And we have a mean squared error, which is the denominator in that formula. So I'm going to call this degrees of freedom denominator. And to use an F table or an F calculator, you will need to know both degrees of freedom. You'll need to know what is a degrees of freedom numerator and what is degrees of freedom denominator. So to determine the probability of an F, you need to know your F value, you need to know your degrees of freedom numerator and degrees of freedom denominator. And when you have those 3 bits of information, you can use an F table to look up the value and determine significance, or you can go online, find an F calculator, or use software that will then calculate the P value for the F. And just like the T, that tells you what's the probability of this result if the null hypothesis is true. And with simple regression, with just one predictor and one outcome, the probability of your F, the P value for your F, will be the same as a P value for your T. So if your probability, if you calculate that probability and it says the probability is 0.03 for t, then the probability of f will also be 0.03. So this is just plugging everything in for our current example where we had looking at people with traumatic bunny incidents, predicting their anxiety. So these are the exact same sums of squares we plugged in, we calculated earlier. We already our degrees of freedom, n minus 1 is 8. N minus number of predictors minus 1 or n minus 2 is 6. And number of predictors is 1. So we have 7, 6, and 1 for our degrees of freedom. And if we take, oh, didn't mean to click that. If we take 320 divided by 1, put a little division sign there, we get 320. If we take 380 divided by 6, we get 63.33, which, by the way, that's the same mean squared earlier when we calculated our mean squared error. That's the exact same mean square we got previously. And so now we take our mean square numerator, 320, the explained variance, mean square, divided by mean square denominator, that's the error sum of squares. 320 divided by 63.33 gives us an f value of 5.05. So that's our f in this example. And then we can look that up on a table or use a calculator and determine what is the p-value for that f if the null hypothesis is true. Now, as I'm going along here, I should call attention to the fact that sometimes people use different names for explained and error. I'm using explained and error. Another possibility is to call explained variance the regression sums of squares, and error, we can call that the residual sums of squares. So those are different names we could apply to those same sums of squares. Sometimes statistical programs like SPSS, when it gives you output, often labels things like regression and residual rather than explained and error. Just note that these terms mean the same thing. Depending on what program you're using, they might call it explained variance or regression sums of squares. They might call it error or residual sums of squares. Those are synonymous terms. They mean the same thing. Which, by the way, when we go on to talk about making group comparisons, we're going to start, eventually we'll use ANOVA to make group comparisons. And when we do that, these names are these are the names that will change at that point. They're going to give, we'll call these different things. We will, other than explain and error, we'll give those different terms when we do group comparisons. But the rest of the math for the table will stay the same. And that is everything up through part 4C.